All right. Welcome back, everyone. We are in 2.6. We're going to pick up where we left off last time after just a quick 30-second recap and very lightly talk about the test. So in 2.6 so far, what we did was the domains, and it's not really going to relate too much to what we're about to do, although what you'll find is a lot of your homework questions will ask for the domains and for you to do the math of adding or subtracting or multiplying or dividing the functions. So again, while I'm treating these as two separate things, you'll find that your homework problems may have you do both in the same problem. It's just like having a part A and a part B. There's nothing that complicates that. You just have to remember your three cases, and then as well as be careful when you have combined cases like D and E that we saw last time, like a radical inside of a rational. And we saw that it mattered whether the radical was in the bottom or the top. It kind of changed how things were gonna work. And this is going to be a problem. My pen is not moving the way it should. So like, if you can see my cursor, I'm all the way at the end of the screen, but I'm only about 25% to the right on my tablet. So I'm sorry, give me a minute. Let me see if I unplug and replug it, if it'll fix it. Perfect, that worked. Technical glitches are fun. Okay, so we had all those examples. Again, not going to spend too much time. If you need more time with that, go back and rewatch the videos. So test 2 is going to be on chapter 2. I know I don't have that typed there, but I've said it several times. We basically have chapter-based tests in this course. So chapter 2 is test 2. It's either going to run the 4th and 5th of November, which is a week from this Wednesday, or it will be the 9th and 10th of November, which is a week from this coming Monday. I am hoping to have this material finished by the end of class on Wednesday. I'm not 100% certain I can. 2.8 is a really short section. What we have left in 2.6 is about enough to fill up a little more than half of the day, maybe. But 2.7 is a little longer. It might take us 75 minutes, which would be one day. It might take us just a touch more. So I'm really hoping to have all of that finished by this Wednesday. If I don't, then I'd have to push the test back. Now, if I get halfway through 2.8 by the end of class Wednesday, I'm still going to have that test be the following Wednesday, because 2.8 is a very short section with really just one concept applied 3 different ways. But let's not waste too much time so that hopefully I can hit the 4th and 5th, because we're a little behind where I'd like to be for our schedule. All right, so same details as test 1. In other words, I will give you a review that will be available in the homework section before your test that I would highly suggest you complete it. Those of you who did complete it saw how similar it was, so that's excellent motivation for doing the review. It'll be 90 minutes. It's one attempt. You'll have 15 minutes to submit your work in Canvas. It'll be located in the same spot as last time. So hopefully we'll have a better feel for things. All right, so we'll talk more about the test as it comes up. But for now, let's get back to 2.6. And we said that we can add, subtract, multiply, divide, and compose 2 or more functions. So I don't think I have to explain what adding, subtracting, multiplying, or dividing is, but I might have to for the composing side of things. But let's try out the first stuff. Well, first. So your basic combinations are, if you're given, I don't really want that in red. I'll actually type it. So if you are given some f of x and g of x, and it could be an h of x and an I of x and a z of x and just a whole bunch of different other functions. It's just saying f is function 1, g is function 2. This is another strength of function notation because they're clearly labeled which one is which, versus having y equals 3x plus 7 and y equals x squared minus 2. If I just say to plug in 3, you go, well, which one? But if I say to do f of 2, you know which one to plug it into. All right, so I'm just going to write out these because the last couple will be too much of a pain to. So if you're given those two functions, if you're asked to do this, f plus g of x, that just says you take the f of x and you add the g of x. The left side is just a slightly annoying notation that I've really never seen a reason to need it, but it exists and it's used, so I have to introduce it to you. But even me as a teacher is going to say, I don't know why anyone ever had this notation, let's just use this stuff. And admittedly, I do know why. It's very complicated reasons that we're not going to get into. All right, f minus g of x, that's too many slashes. That would be take the first function f and then subtract the g function. I will say that almost 100% of people will get the first one right, but then they'll go to the second one and they get it wrong because they mess up distribution of their negatives. So watch out for that. Next up, you might have f g of x. Every time you open up these parentheses, you say of. So f times g of x. Well, that's just the f of x function times the g of x function. Or you might have them on top of each other. F over g of x, and that would just be the first function divided by the second function. These really don't feel like they have a reason to be seen, but that's because of the parameters we have that always make it true. There are versions of math where these things are not necessarily true and it's not as clear cut. Just so you know, there are alternate ways to write these. Instead of writing f plus g, that got a little sloppy, let me erase, f plus g of x, this would be the same thing as just writing f plus g. The same thing for all the others as well, which I will not write all 4 of them. You're more than welcome to. It's just writing it this far right way, writing it this way, doesn't show the variable dependence. So instead of saying f of x, it's just saying f, and then we can assume that the internal letter is whatever we see, or whatever someone else tells it to become later. It's just a matter of whether we're showing the variable dependence. But one thing you need to understand, that all these little things that look like times x's, these little things that look like times x's are not times x's. That is just showing you the variable dependency. So that way, if I said, oh, well, what happens to this thing when it's 3? You just replace the x with a 3. It's not multiplying by an extra 3. It's not multiplying by an extra x. It just shows you what you're plugging in. So again, the others are the same as well. So just understand that maybe in this textbook and with this teacher, you're seeing the parentheses, but maybe with another textbook or teacher, you wouldn't. Or maybe when you go to calculus, because it just gets super tedious writing all these parentheses and of x's, most calculus teachers start trying to drop the variable dependence whenever they can. All right, so for example 1, I guess I should call this example 2, actually, not example 1. I have that wrong in my handwritten notes. That's kind of funny. I usually don't do that. Example 2, because example 1 was earlier. This is example 1 for the day, though. So given that f of x is equal to 4x plus 5, and g of x is equal to x squared minus 2x plus 6, we're going to find the 4 above. So your homework quite often is going to just tell you to find all 4 of these things. Are those the only 4 things we're interested in the world? Absolutely not. I could ask you to find g minus f instead of f minus g. I could ask you to do g divided by f instead of f divided by g. Notice I only said the second and the fourth one there. Because if I asked you to swap the order of the first or third, it won't matter. G plus f is f plus g in the same way that 2 plus 3 is 3 plus 2. F times g is the same thing as g times f in the same way that 2 times 3 is 3 times 2. So the order doesn't really matter for the first and third, but it definitely does for the second and fourth, just based on arithmetic computations. So again, we're going to be finding the f plus f minus f times and f divided by g for all of those. I'm going to run out of room here very quickly, so let's just go down here. Let me, please work. Sweet. All right, you know what? I'm just going to leave it written twice. No harm, no foul, right? Not going to fight word. So for A, that would be F plus G, and I'm even going to write the shorthand version. So again, if I ask you for this, that's the same thing as if I asked you for this. There is literally no difference in me asking for either of these things. I'm going to stick to the shorthand version. So writing F plus G is the same thing as asking for F of X plus G of X. This is not anything new. At all four of these examples we're about to do is literally nothing new. I'm not teaching anything. This is stuff you should have been able to do before today. So we take the F function, which is the 4x plus 5, and then we're going to add the G function, which is the x squared minus the 2x plus the 6. Again, this right here is this right here is this, and then the plus sign between them is still a plus sign between them. All right, so that'll be equal to, well, just combine like terms, put things in a more appropriate order. So the x squared should go first. 4x minus 2x is a plus 2x. 5 plus 6 is a plus 11, and that would be your answer. Again, the actual math, nothing new. It's just injecting that new notation. So f minus g, that's the same thing as asking for f of x minus g of x, which again, we just take the blue minus the red, so 4x plus 5, then a minus symbol, and then we go x squared minus 2x plus 6, question mark. Is this wrong? Is this right? Well, this is wrong, and this is the mistake that more people make than anything else, especially with the subtraction, because this minus has to be applying to the entire function, and right now, it's not applying to all of this. It's only applying to the x squared. So what do? That's right, you got to wrap it in parentheses. So blue minus red, distribute the negative, you get 4x plus 5 minus x squared plus 2x minus 6, because you're changing signs when distributing a negative. Combining like terms, you'll have your negative x squared first if you write them in a more appropriate order. The 4x plus the 2x will be a plus 6x, and then the 5 minus 6 will be a minus 1. And that would be f minus g. Now again, fun fact, if I asked you for g plus f, you wouldn't even need to show me any work. Your answer is the first one. If I asked you for g minus f, however, you would need to do this again. And spoilers, it will just change the signs of all of these in the same way that 5 minus 7 is the opposite of 7 minus 5. All right. How about the product of the two functions, f times g, or written fg in parentheses of x? So that's just the f of x times the g of x. These rewrites are pretty important for us. So that's the 4x plus the 5 times the x squared minus 2x plus 6 question mark. Well, no, same issue. You can't have this binomial times this trinomial and only write a dot. You got to put them in parentheses, and not even just the second one. You need to wrap the first one in it too, because you got to give the 4x and the 5 to that trinomial. Now, some people would say we're about to FOIL this, and some people have the right idea, but the wrong application. You would FOIL this if, say this 6 wasn't here. Then you can FOIL, first, outer, inner, last, because binomial and binomial. We don't call it FOILing if there's more than 2 terms in any parentheses. This is just back to the idea of distribution. And in fact, I want to make these parentheses in black because I want to use the red and the blue strategically to show you the distribution. So in blue, I'm going to distribute the 4x to all 3 of those. So that 4x times the x squared is 4x cubed. The 4x times the negative 2x is a negative 8x squared. And then the 4x times the 6, 4 times 6 is 24, so plus 24x. Now in red, I'll show us distributing the 5. Now you can do it above like that, but it's getting just a little overlappy. So I'm just going to show it below. So the 5 times the x squared would be a plus 5x squared. The 5 times the negative 2x is a negative 10x. And then the 5 times the 6 is a plus 30. Then you're just going to combine your like terms. just going down a line. 4x cubed isn't like anything, so you can write that there. You can cross these out as you use them if you like. I'm not going to leave that up there though. The negative 8x squared plus the 5x squared is going to give us a negative 3x squared. Again, that was this one and this one, just combining like terms. Then the 24x minus the 10x will be a plus 14x. And that was the 24x and the negative 10x. And then we're left with the plus 30 at the end, and that would be our answer. The third one, the multiplication, is almost always the more difficult one. Subtraction is an easy one, but people mess up because they don't distribute the negative or don't put parentheses. This last one should actually be the hardest in general, but based on the material I've taught you and what we assume is prerequisite knowledge, this is going to be simple usually unless you can reduce. But even though long division of polynomials is taught at a developmental level before this course, we don't assume that that technique is remembered. It's kind of interesting what we assume and don't assume is remembered. Can't really say why or why not, but just go with it. This problem is going to look the worst, but it's generally the easiest because you're usually just going to write the one thing on top of the other and you're done, generally. So write the f of x, which is the 4x plus 5, on top over the g of x, which is x squared minus 2x plus 6. Sure, the bottom might be factorable, but it's not. And if it was factorable, maybe you could cancel something, or maybe there was just a GCF in all 5 of these terms that you could cancel and reduce. But none of those things happen, so that's the answer. Again, we have not told you that long division is something you had to have remembered from a previous class. We're going to teach that in chapter 3, in fact. So again, you may have seen it before, as well as synthetic division. But for now, we're going to leave it alone. Now again, just remember that if your answer, if you did a whole bunch of work and you got to something like, I don't know, 2x plus 6 over 6x squared minus 4x plus 10, then what you could say is 2 goes into every single number, so you take 2, you can take 2 out as a GCF, or you can just cross out of each of them. So that's a 1, a 3, a 3, a 2, and a 5, and you'd end up with 2x plus 3 over 3x squared minus 2x plus 5. Which is almost factorable, but it isn't. All right. So let's do one more of these before we get to the composite functions. And let's just go with some weirder functions. So for example, 3, same instructions as last time. We're going to do the plus, minus, times, and divided by. But new functions, now our f of x is going to be the square root of x, and our g of x is going to be x plus 10. So a more complicated style type of function and a simpler linear function. So your f plus g, which again is, if you need to show the rewrites, is f of x plus g of x. I'm going to skip doing that though for the next 3 because I just feel like it's a little tedious. I never skip it for compositions, but I do for these types. So you're, again, just taking the blue thing and adding the red thing as I'm now labeling it. So the square root of x is the blue thing, then a plus. The x plus 10 is the red thing, and blue, red. And there's no like terms. There's no way you could factor this. That's the answer. You do f minus g, that would be f of x minus g of x. That's just taking the first function, which was the square root of x, and then subtracting the second one. Be careful. This is wrong currently because, excuse me, you need a parentheses around that x plus 10 to make sure you're subtracting the entire function. So you distribute that, you get the square root of x minus 10. Nothing can be done there, no like terms. Square root of x and x are not like terms. If I ask for f times g, that would be f of x times g of x, which is just, here's your first function. If you do a dot, this is going to be wrong because look, there's 2 terms. So make sure you put a parentheses around that. Now, the square root of x, nothing can be done there. The x plus 10, nothing can be done there. So if you like a factored answer, this is actually an okay answer. This is an okay answer in a lot of people's books. But some people will say, well, I'm going to distribute it. Square root of x times x, one's out, one's in, so you can't really combine them. just square root of x times x. I just wrote them in opposite order. Then plus square root of x times 10, the 10 goes outside, the square root of x stays inside. Those are not like terms because the first one has an x outside, the second one does not, so you cannot combine them. That is the answer. So again, depending on the context of the problem, if there's a bigger fish to fry here, maybe you want to leave it as the first one. Maybe you actually don't even want to distribute it, but maybe you do. It would depend on, again, context. Finally, f over g would be the square root of x over x plus 10. Again, literally, you can't do anything to that. But I do want to point out that if it had been upside down, g over f, that would have been x plus 10 over square root of x. If you box this up, it's wrong. You go, well, wait a minute, Mr. Beckner. Why is the f over g right, but the g over f wrong? Is it because the bottom only has one term? That's actually a good guess, but no. It's because you can't have square roots in bottoms. We've discussed this previously. It was one of those review topics, prereq topics, that we said you should focus on in your own time, but you have to rationalize the denominator. We saw this with complex numbers where we multiply top and bottom by the complex conjugate of the bottom, but this is just a single term, which means you just multiply top and bottom by what that radical is. And what that would end up giving you is, in the bottom, square root of x squared. In the top, you actually get exactly what you have for either of these for the f times g. So I'm just going to write the square root in front. In the bottom, the square root of x is x. No more square roots, so we're good. So you could have this as an answer, or you could have distributed that square root and had your x square root of x plus 10 square root of x all over x. Again, it just depends on whether you want your top distributed or factored. There's reasons to factor things, there's reason to distribute things. Just depends on context. But again, what was important to understand about this problem is you couldn't have the square root in the bottom. That would not have been simplified. And if you're going on to trigonometry, that issue will continue to come up. If you're going on to calculus, that issue will continue to come up. All right. So again, no real new arithmetic in any of these problems, just kind of relabeling them with function notation and combining them. And the cool thing about this is if I give you an h of x also, you could do f plus g plus h, or you could do f times g times h. And you don't have to use all of the functions, you can just use f and h, or you can use the same function twice, f times f, or g times g, or h minus h, which would be 0, but you know, not the point. All right, so let's get on to the real bread and butter of dealing with these functions, composite functions. And again, this is another thing that you should have been taught in a course before this, but we don't necessarily assume that you remember all of it. So this is kind of de-rusting, going a little quicker through it, but still calling it pre-calc material. There's a lot of overlaps in math. So composite functions. I call this the chicken cordon bleu of math. What's chicken cordon bleu if you're not aware? It's where you take a piece of chicken, that should be obvious, and then you stuff it with some other things inside of the chicken. So you cut it open, you split your chicken, and then you put cheese and maybe ham or bacon or whatever. And I guess chicken cordon bleu is probably traditionally just ham and cheese inside, but you could put other things. You've got like your turducken, a turkey and a duck and all, and whatever else. Turkey, duck, chicken, yeah, turducken. You can put one inside of the other. I'm assuming you would put the duck inside of the chicken, inside of the turkey, just based on size. Might get a little weird otherwise. So with your chicken cordon bleu, let's just go back to the ham and cheese and chicken concept. The ham and cheese is one function, the chicken is another function, so we're taking ham and cheese, one function, and putting it inside of another function. And you can do this over and over and over, just like the turducken. You can put one function inside of another function inside of another function. And you can do your algebra and arithmetic in various ways, but you'll see me do things primarily one way, and that is, if you're given two functions, so chicken and ham and cheese, So in the real world, you're probably not going to put a chicken inside of ham and cheese. I mean, I guess you could just wrap the chicken in a giant piece of ham and cheese or something like that, or staple it on. I don't know. Don't eat staples though, please. So at least in math, it'll make a little more sense. Yeah, in the world, we probably only do this one of the ways, but in math, you could put the F inside of G, or you could put the G inside of F. You could put a chicken inside of another chicken, so you could put F inside of F. You could put ham and cheese inside of other ham and cheese, so G inside of G. But here's the concept. Replace the inner function with what it actually is. So what it is somewhere you have g of x equals x plus 10. So you would replace where it says g of x, you would instead write x plus 10. That's basically what I'm saying there. Then after you've done that, you replace the x in the outer function with what is inside the parentheses or brackets. I prefer brackets personally because you'll have parentheses inside of other parentheses otherwise. Replace the x in the outer function with what is actually inside of it. This right here is the same exact step of any function evaluation. If you want to do f of 2, you replace the x from the f function with 2's. If you want to do f of x plus h, you turn the x's into x plus h's. So the letter outside tells you which function to go to, and the thing inside tells you what to replace it with. And the thing is, the thing that's inside in step 2 is whatever you just replaced in step 1. So I had said, all right, turn the g into x plus 10. That's what you're going to make in your x's in the next step, but you're going to be plugging into the f function probably. And then from there, you just do your algebra and arithmetic. Then I have a little memo that says, if you have a problem where if the composition has a number inside instead of just an x, you're going to want to substitute that into the inner function first, and then you'll have another number, and then you'll take that number and plug it into the outer function. You will see an example of this, which is why I just rushed through saying it. We'll come back to that concept. Let's focus on dealing with just pure x's first. And we're going to borrow the function from example 2. So we're going to go back to these, the 4x plus 5 and the x squared minus 2x plus 6, but now we're going to stuff them inside of each other. So for example 4, given f of x is 4x plus 5, and g of x is equal to x squared minus 2x plus 6. That looks like a g because I was about to say g. Let's find f of g and g of f. So we're going to do that. Now, we're going to show you the notation just inside of the problem. So your notation, we're going to find f of g of x, which I'm going to rewrite in the notation here, but I'll just leave a little space, about the same amount of space as writing that. And then for b, we're going to find g of f of x, which again I'll rewrite here. So earlier I said with the plus minus times, I didn't really see a reason why these pure mathematicians want to write f plus g of x when you can just say f of x plus g of x. I don't really see a reason for the rewrite except in very complex math that we're not doing in here. The same idea here, except when you're getting into like 300, 400 level mathematical concepts. There's no real reason to write this way, but I still have to introduce the notation. I don't like it, but I'm going to introduce it either way. So what you should do is the rewrite for this goofy notation, these little O's, it kind of looks like fog and goth. And the O is not on the same height as the F and G. It's kind of raised. And I'm always very bad at doing that. It looks a little better for the golf one. But this O just tells you to say of again. So this is read f of g of x. This is read f of g of x. But this would be a lot better written as f bracket g parentheses x. Because every time you open a parentheses or a bracket, you say of. So this says f of g of x. It's read the exact same way. But now you can see that g of x is the inside and that the f of whatever is the outside. It makes it easier to tell what's the inside and what's the outside because written this way, I can't tell what's in and what's out. So you actually read these or process these in a right to left manner. And that's what feels weird to a lot of people at first. You process these in a right to left manner. You do the g of x, then you do the f of whatever it says. Conversely, for g of f of x, this would be g bracket f parentheses x, which would be read out loud the exact same way. G of f of x. All right, so focusing on a first. We're doing f of g of x. And again, do you have to have all that other stuff? No, you could just write it this way too. That's the same thing, I'm just not showing the variable dependency. But we already kind of practiced that way before, so let me show everything. So what do you do first? You do the rewrite. You write it this way because you can tell what's inside and what's outside. If you want to use parentheses instead of the brackets, be my guest. Plenty of people do it that way. My eyes just aren't the best, so I've always done it this way. So first step, replace the inner function with what it is. Replace the inner function with what it is. So we are going to replace the inner function g of x. Let me pick a different color. We're going to replace this thing with what it actually is, and g of x is actually x squared minus 2x plus 6. So this becomes f of, and you could change this to a parentheses if you wanted, since there will be no more, and then x squared minus 2x plus 6. See, the g of x is actually this thing, so I turned it into the thing it actually is. Now, what we're going to do is we go to the f function. This says, where do I plug it in? This tells me where to plug it into. If I just saw f of 6, if this is all I saw, you would turn this x into a 6. That's all you do. But, I did unmute, yes, okay, good. But that's not what it says. It says f of blah, 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 like an f of x plus h. So this x has got to turn into all of this stuff. So instead of going 4x plus 5, we go 4 blah, 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 everything that I just circled, and then a plus 5 after it. So this is going to become 4, I'll use red for the replacement, so this x right here becomes, again, this x right here becomes what's inside the bracket, x squared minus 2x plus 6, and you obviously need a parentheses for that, and then a plus 5. So again, it was 4x plus 5, but we were told to plug in this, so 4 times this plus 5. And then all we do from here is distribute, FOIL, combine like terms, whatever we have to. So that'll be 4x squared minus 8x plus 4 times 6 is 24, then a plus 5, which is 4x squared minus 8x plus 29. That would be our answer. That is stuffing one function inside of another. That is our chicken stuffed with ham and cheese. Now you might say, well, Mr. Beckner, why do we ever need to compose functions? Because a lot of things in the world are based on somebody does something, hands it off to someone else. They do something, hand it off to someone else. They do something, hand it off to someone else. That's what this is. All right, so let me erase my little circles and stuff so we don't confuse you for part B. Now we're going to do it the other way, g of f. And I love doing these both ways because going back to the add, subtract, multiply, divide, we said adding and multiplying, order doesn't matter. Subtracting and dividing, the order did matter. So we're going to find out whether the order matters for compositions. So first do the rewrite. This is the better way. This is the only way we should really have to do it at a pre-calc level, but it is what it is. Then we say, all right, we first replace the inner function with what it actually is. Replace the inner function with what it is. Replace this function with what it is. What is it? 4x plus 5. So this becomes g of and then the 4x plus 5. How did I know to replace it with 4x plus 5? Because it told me to. If that said g of 2, I would just be plugging 2 into the g function. This would be a much simpler problem. All right, so now we go to the g function, which is here, and we're going to replace its x's, and there's multiple x's. We got one here and here. Both of those x's are going to get replaced with this entire 4x plus 5. Again, both of these x's will get replaced with 4x plus 5. See, I knew to go to the g function because that says g. So we're looking at this thing. Then we replace its x's with whatever is inside. If it just said g of 5, then that would be 5 squared minus 2 times 5. All right, so the x squared, it's going to be something squared, but we got to square the 4x plus 5, which means we got to wrap it in parentheses so it squares appropriately. Then the minus 2x, that's minus 2 times what we're replacing it with, 4x plus 5. And then the plus 6 at the end stays a plus 6. There is no x to replace there. All right, we got our Madden drawing going. So now what we have to do is just clean this up. Well, this 4x plus 5 is being squared, so you got to write that as 4x plus 5 times 4x plus 5, which you'll have to FOIL next. We can distribute this negative 2. I'm going to go ahead and do that. So that's minus 8x minus 10. Then the plus 6 stays at the end. We're going to have to FOIL the 4x plus 5 times the 4x plus 5. You should be masters of foiling at this point. 4x times 4x is 16x squared. The 4x times the 5 is a plus 20x. The inner, 5 times 4x, same thing. I missed my 0. And then our 5 times our 5 is a plus 25. Bring everything else down. Minus 8x. You could go ahead and combine the minus 10 plus the 6 if you want to. That's up to you. I'm going to save it, though. That does say FOIL, not fail. So 16x squared, 20x makes 40x. 40x minus 8x is going to be a plus 32x. Then we have our 25 minus 10, which is 15. 15 plus 6 is 21. And that would be our answer. Let me go back and erase my Madden circles and arrows and all that jazz. It just doesn't make any sense after. What's going on? That was weird. All right. So note, f of g was not the same thing as g of f, so the order matters. When we did it one way, we got a different answer from doing it the other way. Spoilers, doesn't always happen. Sometimes they're the same. And sometimes when they are the same, they're this magical answer. And when they're this magical answer, then those two functions are related in an extremely important way. It's rare, it's very rare to just be given two functions and they have this special relationship. But quite often in math, what we'll do is we'll start with one of them and we'll find this other special function by doing a process. That'll be the next section in 2.7. So let's not spoil too much of the fun for now, but just know that this composition stuff isn't going away. It's gonna come back. All right, so one more. Example 5. Excuse me. So let's say for f of x equals square root of x, and we're not going to do the exact same problem as example 3, for the functions at least, x squared plus 9, and I did say 3 intentionally. So we did a square root function previously, but the second one looked different. I think it was just x plus 10. Now it's x squared plus 9, and I do that for a reason. We're going to do the exact same as last time. For a, we're going to find fog. f of g of x. And then for b, we're going to do g of f of x. These are not the only two things I can ask you for. I could ask you for f of f. I could ask you for g of g. I could ask you for f of g of f of f of g of f of f of g of f. I would never do that last thing, but maybe you live in a real world context where that's just a problem you got to do. Just, you know, the boss's boss's boss says something to the boss's boss, and the boss's boss says something to the boss, and then the boss says something to you. They're all handing things down, and they probably process them in some way. They functioned, just not mathematically necessarily. All right, so the rewrite. f of g of x. Now we're going to replace the inner function with what it actually is. So this is f of x squared plus 9. So that says we go to the f function, and we're going to replace its x's with what's inside. So this x is going to turn into x squared plus 9. I circled the wrong thing at first. I just meant to circle this. Boom. So instead of square root of x, we're going to write square root, but instead of x, we write that red ink, the x squared plus 9. Now, yes, the square root of x squared is x. The square root of 9 is 3. But with a sum between them, you can't do that. This is the answer. It's possible that the inside would be factorable. If the inside was factorable and they were the same factor, then you'd have the same thing squared, and then the answer would just be one of those terms. I will make that note after finishing B. Now let's do g of f of x. Okay, so that's g bracket f of x. Let's erase all my Madden stuff. Got a little too erasey. Erasey, there we go. So then we replace the inner function with what it is. The inner function is f of x, so we replace it with square root of x. So this is g of square root of x. And then that tells us to go to the g function, which is up here, and we turn its x's into whatever is inside the bracket, square root of x. So this is going to be the square root of x squared, then plus 9. See, the x here has turned into a square root of x. It wasn't a multiple term thing to plug in this time, so it looks too simple almost, but this is right. Now last time we were done because square root of x squared plus 9 with both of those in, and with a plus sign, you can't just take those square roots independently. But this is completely different. That square root and square part are by themselves. Square roots and squares cancel that way, so the first bit is just an x, and then a plus 9. Now, admittedly, some people might throw in an absolute value sign with this based on whether x is allowed to be negative or not. We're not going to get into all of those crazy details. If for some reason a test question marked you wrong because you didn't put an absolute value there, I would go back and give you full credit for that. But I do not believe that that will be an issue for the test. I pick my problems accordingly. A homework problem, maybe just learn for that one problem. But there's this thing about square roots and squares. If you allow x to be negative, then that answer is not technically true, but we just kind of fly with it. Because whenever we deal with square roots and squares all kind of paired together in higher math, we tend to just say, oh, we'll make x positive anyways. So we can eliminate that goofy case. All right. So that will finish out 2.6. We have the domain, I was about to say range, and we did not do that. We just had the domain. We did the domain of polynomials, rationals, and radicals. We said polynomials don't have any of that goofy stuff in them. Rationals have fractions with variables in the bottom. Radicals have square roots, cube roots, fourth roots, whatever. We had the three cases we told you to memorize. We gave you reasonings for them so that it's not just memorization. So if you don't memorize them, you can go, all right, well, what's the logic behind this? Why was it this way? That's the way we're trying to teach you in pre-calc. It's not just to memorize, but to understand the why and the how when we can give you the why and the how. Lots of examples of those. We added, subtracted, multiplied, and divided functions. We composed them, we chicken cordon blued them, we stuffed them inside of each other, and we got different answers. That did not finish the section. I forgot to do something. I just realized that. I'm going to call it example 6, but it was supposed to be part. Oh, shoot. That really stinks. I came to the end of the page, and if I do this, oops, I did the wrong thing. Insert page. Oh, no, oh, yeah, I did it wrong. Okay, so I'm just gonna have to do this on another page. Sorry about that. Undo. So we're up to example 6. Sorry, this is still 2.6, as I said. I missed these. Example 6, going back to the functions from example 4, which were 4x plus 5, and x squared minus 2x plus 6. We're going to do f of g of 3. That'll be a, and then b, I'll write it later, we'll do g of f of negative 3. So not the same number, but going back to what we said previously, if the composition has a number inside instead of x, you'll want to substitute that into the inner function first. So we're still working in to out. We're still working right to left, if you will. But now it's not going to be nearly as goofy looking because it's just going to be plugging one number in to get another number and then taking that number and plugging it in to get a final answer. So f of g of 3, do the rewrite. That's f of g of 3 that way. So now what we're doing is we're going to find what g of 3 is. See, before this was g of x. Before we were doing x, and we couldn't evaluate it for x because, well, it's right here. So that was why we just replaced it. But now we got to find out what exactly is g of 3. So what a lot of people will do is they'll go to the side and they'll say, well, g of 3 would be 3 squared minus 2 times 3 plus 6. How did I know not to plug it into f? Because it says g. Well, it says f here, Mr. Beckner. You're working right to left, though, student. The 3 squared is 9. The 2 times 3 is 6. The negative 6 and the positive 6 will end up canceling. So you end up just getting a 9 there. So g of 3 is equal to 9. G of 3 is equal to 9. So this g of 3, we're going to replace with 9. It's not going to be g of 9. We just replace the g of 3 with 9 because that's what g of 3 is. So this is equal to f of, and again, you can swap that to parentheses if you prefer, 9. Now that just tells us to go to the f function and plug in 9. So we're going to turn this x right here into a 9. This is 4 times 9, then a plus 5, which is 36 plus 5, and that's 41. So that's the answer. I knew it felt like I missed something when I was talking about this. All right, last problem of 2.6, I promise. G of f of negative 3, do the rewrite. So we're going to find out what f of negative 3 is first. We got to find that. I'm not switching color for any poetic reason. I'm just switching it for visual sake. Oops, not yet. So we got to find that. So to the side, our f of negative 3 is 4 times negative 3 plus 5, which is negative 12, plus 5, which is negative 7. So this negative 7 is what's going to go there. Instead of f of negative 3, we just write negative 7. So now this is equal to g of Again, parentheses if you prefer, no one cares, -7. So we're going to the g function, and both of the x's will turn into -7s. So that's going to be -7 squared, and then minus 2 times -7, and then plus 6. Again, x are replaced with -7 and -7. The -7 squared is going to be +49, and that's a plus 14 plus 6. It's easier to add the 14 and 6 to get 20. 20 and 49 make 69, and that will be our answer. Now, here's a cool feature, though. We already knew what f of g of x and g of f of x were written as functions. They were, I don't want it to keep flipping back to the screen, so hopefully you're taking good notes, students. For a, the f of g of x was 4x squared minus 8x plus 29. So here's something cool. Knowing that that composition is 4x squared minus 8x plus 29, I could actually have just taken the +3 and plugged it in there, and guess what? The answer would have been 41. But if I didn't do that first, if I just straight up asked for f of g of 3 without asking for f of g of x first, you would definitely want to do it this way for efficiency. But the point is, 2 ways to get it done if you choose to do it the other way. Conversely, for g of f of x, we found that to be 16x squared plus 32x plus 21. If you plugged it -3 into that, because b asked for g of f, you would also get 69. So that's just a time-saving element, and there are homework and possibly test questions that do that. Again, what I had is example 4 and example 6. I meant to have it as one long problem. That was on me for skipping it. My piece of paper was covered up, so it just got missed. I got excited to get to the next one. But we completed it, so it doesn't matter, and it also proves the point that they don't have to be part of the same example. All right. So on that note, we have now finished 2.6, and we can now continue with 2.7, which I have as a new file over here. Let me make sure I give myself lots of space at the end so that doesn't happen again. All right. Inverse functions. So this is going back to the idea previously. This will be back in a second. We said that when we did A and B from example 4, that the answers did not turn out to be the same thing. The one composition wasn't the same as if you did it backwards. So the order mattered. But I also mentioned that sometimes you do get the same answer, and that when that happens, it means that maybe something cool is happening between the two functions. So if you do the composition one way, and you get the same answer as doing the composition the other way. And so it's not just that these two things are identical. It's not just that f of g is the same thing as g of f. It's that the answer turns out to be x. This has to be the answer both times. When you do f of g of x, you have to get x. When you do g of f of x, you have to get x. If that happens both ways, then they are this magical property known as inverse functions. One function is the inverse of the other. You have been dealing with inverses all your mathematical lives, you just may not have known it. We didn't call them inverse functions though, we called them adding and subtracting. Those are known as inverse operations, and an operation is a type of function. Or we call them multiplying and dividing. Multiplying and dividing, some people call them opposites, but they're reciprocals or inverses of each other. Squaring and square roots are inverses of each other. Spoilers for chapter 4, exponentials and logarithms are inverses of each other. And I'm not even going to go into other classes of functions. So if you have two functions, you're staring at two functions and you go, I suspect they're inverses. Well, let me do the composition, and if both of those turn out to be x, then I know they're inverses. Or maybe your teacher just says, hey, here's f and g, find out if they're inverses. So that's what we're going to be doing in our first example. We're going to show that two functions are inverses of each other. Now, I bumped this down not quite enough. Far enough, there we go. So we just wanted to look at that line. So for example 1, verify if f and g are inverses. For A, we're going to have f of x be equal to 2x plus 5, and then g of x, we're going to let be x minus 5 over 2. So one method of determining if two functions are inverses, notice I said one method, is to do the composition both ways. Do not think that you can just do it one way. Just because you prove one of them is x doesn't mean that the other way is x. It is entirely possible and probable that it might be x one way but not the other way. And it could be as simple as one way it's x and the other it's plus or minus x because a square root of a square canceling blah, 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 blah. So yeah, that wouldn't be inverses. Okay, so we're going to do f of g of x, and you're going to notice that I'm no longer showing that open circle notation because I don't like it and don't think we need to see it over and over and over. So f of g of x this way would be f of, replace the inner function with what it is, and that's x minus 5 over 2. Still like the color though, because it helps with eyes. So that tells us we go to the f function. See, we're done with that now. We're going to the f function now, and we're turning its x into all of that, x minus 5 over 2. So this is 2 times x minus 5 over 2. Now you could argue this is written right, you could argue it's written wrong. It depends on if this 2 is placed to the side or the top. Kind of looks like it's the side, but what you may even want to do is just put this in parentheses to be super careful. Arguably you don't need it because of the fraction, but again, it's just me being careful. But then there's this plus 5 out to the side. So that's the composition, that's f of g. Then we just clean this up, and there's a lot that can be cleaned up here. There's a 2 in a top, there's a 2 in a bottom. Those are going to cancel each other out. So that's just x minus 5. I'm going to kill the red though. And I don't need the parentheses because the 2's aren't there anymore. Then a plus 5 and the minus 5 and plus 5 will, yep, cancel each other out, and you get just an x. All right, well, they're inverses. My answer is x, right? No. Careful. You are halfway to showing that they're inverses. To show that they're inverses, you have to do the composition both ways. And this is another one of those topics where I say, all right, if the question on a test is just are they inverses, yes or no? If you say yes and it's right, I might go to your work and say, well, you didn't show me why they're inverses, so I can take points from you. So show your work. Don't forget that. Showing your work is always critical at this level. All right, so g of f, replace the inner function. So we're going to replace the f with what it is, and it's 2x plus 5. Then that says to go to the g function and turn its x into everything inside the brackets, 2x plus 5. So this will be, well, that x is this 2x plus 5 now. Again, this x is the red ink I just wrote. But then after that x, there's a minus 5, and then the whole thing is over 2. Now, if you do this right here, that is technically not correct because the 2 doesn't go into those 5s. Ultimately, they will cancel each other out, but that's because of something else. The 5 minus the 5 cancel, so that's just 2x over 2, and because there's no pluses or minuses, now those 2's do cancel directly, which is just an x. So this was good, this was good. They're both exactly what we wanted them to be. They match and they're both x, thus they are inverses. So f, oops, that was not what I meant to do. So f and g are inverses. Now, adding and subtracting are inverses. Multiplying and dividing are inverses. Square roots and squares are essentially inverses. Exponentials and logs are inverses. But what does it mean for a function to be an inverse? Well, you saw it typed up for a brief second, and we'll come back to it, but it just means that the inputs and outputs have been swapped. So like adding and subtracting, it's like you did the opposite of it. So with functions, the opposite is like swapping the inputs and the outputs. The x's become y's, the y's become x's. Or all of the coordinate pairs, their x's become whatever the y values were, and their y values become whatever the x values were. Before officially getting into that though, let's do one more of these. And let's go with f of x equals 7x plus 3. That looks like 7 plus 3, doesn't it? That's bad, Rodney. 7x plus 3. Then g of x, we're going to have be 7x minus 3. And I'll see a lot of people, if the question is just, are they inverses, yes or no, that, oh, 7, 3, 7, 3, there's a plus. Yeah, they're inverses, yes. And then they move on. And then it turns out that maybe they're wrong, because don't just guess on this stuff. Do the work, do the legwork. It's the only way you're going to prove it's right or wrong. But what people will end up doing is they'll say, oh, well, this had a 2, there's a 2, there's a 5, there's a 5. So I see 7s and 3s with pluses and minuses. So yeah. But let's actually see what happens. And you probably already know what's going to happen in terms of the final result. But let's do the legwork. Let's do these compositions. So f of g would be f of the 7x minus 3. So we go to the f function and turn its x into what's inside the bracket, and that's 7x minus 3. So this is 7, then times the red ink, then a minus 3. Plus 3, plus 3, plus 3, excuse me. Again, the core of this is what I'm writing here. It's just the x turned into the red ink. I just almost made a visual mistake is all. All right, we'll distribute the 7. You get 49x, then minus 21, then the plus 3. And that's 49x. Negative 21 plus 3, is that a negative 18? I feel like I said that as a question, but I didn't mean to. It is negative 18. And I don't know why I boxed it up either, because I was correcting myself, doing too many things at once. Well, first of all, this is not equal to x. It does not even matter what g of f is. We can skip g of f of x. It might turn out to be the same thing as f of g, but it doesn't matter because it wasn't this magical answer of x. And I'll give you a reason later, probably next class, as to why it's x. But for now, I'll just take it as a leap of faith. The basic idea is that y equals x, swapping them would give you x equals y. It doesn't really change anything, but it does to a core. So, are these inverses? No. F and G are not inverses. They do not share that very special property. Very, very, very special property. Now, this is not the only way to prove that two functions are inverses. We will, let's see where time is. There is a second way. We will go over it maybe today, maybe next class. All right, so inverse functions, as I briefly mentioned earlier, have swapped coordinate pairs. In other words, to find an inverse function, not me giving you two functions and asking are they inverses, me just giving you an original function, just one of them, you can find its inverse by swapping every single coordinate pair's x and y's. So what I'm saying here is, let's say your f of x was just denoted by this table of values, 0, 1, and 3, 9. That's the entire function. The inverse of f of x would just be 1, 0, and 9, 3. You literally just change the x and y pairs. You swap them. Don't overthink it. That is the entire concept of inverse functions. It swaps x and y's as coordinates or as variables or it swaps up and down with left and right as a graph, because up and down is y and left and right is x. Inverse functions have swapped coordinate pairs. You're just changing out all x's and y's. Now, if I just give you a graph and you say, all right, well, I want to find its inverse, it doesn't always have an inverse. Just like all graphs aren't always functions. So all graphs are not always functions because they could fail the vertical line test. Well, all graphs don't always have an inverse function because when you invert it, that thing could fail the vertical line test. So you could have something that's originally a function, it passes the vertical line test, but when you swap all the coordinate pairs to identify its inverse, that thing may not pass the vertical line test. And if it doesn't, then while the original function was a function, the inverse wouldn't be a function. So you couldn't say it has an inverse function. So that's what this is relating to. A function is one-to-one if no outputs are repeated for different inputs. This is like the test for being a function, but reversing the input-output words, because inverse reverses the input and output words. So we said something was a function if all inputs had the same output, basically. A repeated input could not have different outputs. This says repeated outputs cannot have different inputs. So again, it's kind of flipping the script on the function test. But anything that is one-to-one, anything that passes this, that repeated inputs don't have different outputs, repeated outputs don't have different inputs, so it's a two-way street now, that function would be invertible. Sorry, I don't want to scroll too fast. That got a little uglier. Do that one. There we go. Okay, so given an f of x, so given some function, and I have to give you a function. I just can't give you an equation and ask for its inverse. You have to know that it's a function, or you have to be able to determine that it's a function. If you have something that's not a function, you can't find an inverse function because the first thing wasn't a function. The inverse function is only true if the first thing was a function to begin with. So given some function and you know that it's one-to-one, either the teacher tells you or my math lab tells you, or you determine it based on a vertical line test and what we'll call a horizontal line test, as we'll see later. An inverse function can be found by this method. First, you have to write the f of x as y. If you don't, I can guarantee you you're going to have a very difficult time because of the second step and the third step. We have talked about how f of x and y are synonymous. They are the same thing essentially, except f of x is a little more focused. We can do more things with f of x. Well, to find an inverse function, the math that we're going to have to do, it's a lot easier if we just write it as a y instead. So we're going to make it a y as a placeholder, but ultimately we will come back to this f of x style notation. So just change your f of x to a y to make things easier. Then we said the entire concept of functions being inverses is you swap the x and y's, whether they're coordinate pairs or literal variables. So that's what the second step is. To find the inverse, we're swapping the x's and y's. It's kind of like if you have an x plus 4, to move the 4, you subtract it because that's the inverse under addition. We're talking about inverse under functions. It's more complicated. So swapping the plus 4, the minus 4 is kind of like swapping the x and y. Once you swap your variables, then you solve for y via your traditional methods. Everyone should be able to solve all the ones we give you. There might be a kind of complicated one, but you should still know how to solve it based on stuff we've taught you. But once you get down to a y equals blah, 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 blah format, you are not done And it's another one of those cases where my math lab makes it a little too easy and it goes ahead and puts it in the notation. But you have to write F inverse of write F inverse of X instead of Y. That is the final step. You're not supposed to have Y equals. You're supposed to have that function notation in the answer because the original thing had function notation. But you don't just write F of X because that would be calling it the same thing. You need to call it something else, and we call it F inverse. And this poor word format should look like this. Instead of Y, you're writing this. It looks like F raised to the -1. No, that does not say reciprocal. That is the notation for an inverse function. There's a lot of overlapping symbols as we've discussed previously. So again, this is not 1 over x. So note that F inverse of x is not the same thing as 1 over f of x traditionally. That is not the same thing. It would have to be written this way. That would be 1 over f of x. And you really don't see that in this course, so please don't think you will. But again, F inverse of x, or the inverse of f, is this notation right here. You have a little -1, it looks like an exponent over the f. So the last thing I want to say, that's for much, much later, is that if you're given f of x, and its inverse function exists, the inverse of f of x is, again, this is just kind of rewriting what I said already, f -1 of x. That's read as f inverse of x. Note, for example, 1a, because they were inverses of each other, you could say that f of x was the inverse of g of x, or you could have said that g of x was the inverse of f of x. It's a two-way street. It's a yin and a yang. It's a coin. It's heads and tails. Think about a coin. If you got it heads up, you flip it, you're on tails. That's the inverse. You flip it again, you're back to heads. Heads is the inverse of tails. Tails is the inverse of heads, excuse me. So when you have two functions, an f and a g, you could say that f is g inverse, or you could say g is f inverse. Because when you swap x and y, you're on the inverse. When you swap it again, you're back to the regular function. It's a mirror, it's a coin, it's a two-sided thing. And that is as far as we'll get to today. So when we come back to class on Wednesday, we will pick up with these instructions. We'll take 30 seconds to reiterate them, and then we will go and do example 2, which will be several of these where we're just given one function and we have to find the inverse. All right, so we did finish 2.6. That homework is due in 1 week. I'll have that date edited later today. So again, 2.6's homework is due, sorry, I'm trying to pull up my calendar. Today's the 26th, so the 2nd of November. So 2.6 is due November 2nd. 2.7 will finish next class. I think we'll finish 2.8 as well next class, and then we can have our test on the 4th, but we will confirm all those details, you guessed it, next class. Have a good day. Email me if you have any questions. Take care, everybody.